When you look up at the night sky, the universe can appear as a static, silent tapestry. But hidden in that darkness, incredibly violent forces are reshaping the very fabric of space-time. On August 17th, 2017, a signal reached Earth that shattered everything we thought we knew about the cosmos. It was the echo of a cataclysmic event that occurred 130 million light years away, an explosion so extreme it literally manufactured the gold in your jewelry. But how did this single, fleeting flash of light solve four of the biggest unsolved mysteries in modern physics all at once? How did it prove Einstein right, pinpoint the origin of the heaviest elements, and offer a brand new way to measure the expansion of the universe? And what exactly happens when two of the most extreme objects in existence finally collide? We are going to explore the landmark detection of GW170817, revealing the mind-blowing energy of colliding neutron stars and how this one event completely changed our understanding of the universe. To truly grasp the magnitude of what happened on that day in 2017, we first need to travel back in time and understand the sheer absurdity of the objects involved. For decades, astronomers have studied the life cycles of stars, mapping out exactly how they are born, how they live, and ultimately how they die. When an average star like our Sun reaches the end of its life, it goes out with a relative whimper, shedding its outer layers and leaving behind a glowing, dense core known as a white dwarf. But for stars that are much more massive, between 8 and 25 times the mass of our Sun, their death throes are spectacularly violent. When these giants run out of nuclear fuel, their immense gravity causes the core to collapse inward at a significant fraction of the speed of light. This collapse triggers a massive shock wave that blows the outer layers of the star away in a Type II Ib or Ike supernova explosion. But it is what happens to the core left behind that pushes our understanding to the limits. The gravitational pressure is so intense that the very atoms making up the core are obliterated. Electrons are violently crushed into protons, fusing together to create a dense, degenerate soup of pure neutrons. The result is a neutron star. These objects are the ultra-dense remnants of dead stars, and they are, without a doubt, the most extreme natural laboratories in the universe. To understand just how extreme they are, we have to look at their physical dimensions. A typical neutron star packs roughly 1.18 to 1.97 times the mass of our entire Sun into a sphere that is only about 12 miles, or 20 kilometers, in diameter. That means you could comfortably fit a neutron star within the city limits of Manhattan or Chicago. But because so much mass is crammed into such a tiny volume, the density is almost incomprehensible. A single teaspoon of neutron star material weighs approximately 1 billion tons. To put that into perspective, that is more than the weight of all humanity combined, crushed down to fit on a single piece of silverware. Their density is approximately 100 trillion times that of water, perfectly matching the density of an atomic nucleus. In a very real sense, a neutron star is essentially one gigantic atomic nucleus floating in space. And with that unimaginable density comes unimaginable gravity. The surface gravity of a neutron star is roughly 200 billion times stronger than what we experience here on Earth. If you were to drop an object from just 1 meter above the surface of a neutron star, it would hit the ground in a microsecond, accelerating to millions of miles per hour. But it gets even stranger. Some neutron stars, known as pulsars, spin hundreds of times per second, emitting lighthouse-like beams of radiation as they rotate. Others possess magnetic fields that reach between a trillion and a quadrillion Gauss. For comparison, Earth's magnetic field is just 0.5 Gauss. These highly magnetized variants, called magnetars, are the most strongly magnetized objects known to science. Deep inside these cosmic heavyweights, the physics becomes so bizarre that scientists are still struggling to understand what state the matter actually takes. The internal physics is described by something called the equation of state, which links pressure to energy density at these extreme limits. Finding the true equation of state is considered the holy grail of neutron star research. Theories suggest the core could contain exotic particles like hyperons, kaons, pions, or even a frictionless sea of free quarks, creating hadronic superfluids and proton superconductors. These are conditions utterly impossible to recreate in any laboratory on Earth. So, if a single neutron star is this chaotic, what happens when you put two of them together? When two massive stars exist in the same binary system, they orbit each other for millions of years. Eventually, both stars explode as supernovae, and if the system is not torn apart by the blasts, the two surviving neutron stars become locked in a gravitational dance. Over thousands to millions of years, the orbiting pair slowly loses energy by radiating invisible ripples into the fabric of space-time, known as gravitational waves. As they lose energy, their orbit slowly shrinks, bringing them closer and closer together. This orbital decay was first proven indirectly by Russell Hulse and Joseph Taylor, who won the Nobel Prize in 1993 for observing a binary pulsar system slowly spiraling inward. We knew that eventually these pairs had to collide, but observing the actual collision of two neutron stars remained entirely out of our reach. That is, until the morning of August 17, 2017. At exactly 12:41 04 UTC, an alert triggered across the global network of gravitational wave observatories. The signal arrived first at the LIGO Livingston detector in Louisiana. 3 milliseconds later, it washed over the LIGO Hanford detector in Washington state, and shortly after, a much fainter trace was picked up by the Virgo detector in Italy. This signal was assigned a rather clinical name, GW170817. But there was nothing clinical about what the data showed. When scientists convert gravitational waves into audible sound, they refer to it as a chirp. When LIGO detected its very first black hole merger in 2015, the chirp lasted for only a fraction of a second, a brief millisecond thud as the two invisible behemoths swallowed each other. But this new signal was completely different. It lasted for approximately 100 seconds. For nearly 2 minutes, scientists listened as the two neutron stars spiraled inward, their orbital speed increasing dramatically as they closed the final distance. As they accelerated, the gravitational waves increased in both frequency and amplitude. The pitch rose steadily, acting like a cosmic crescendo that ended in a final, violent merger. This exceptionally strong, clear signal had a signal-to-noise ratio of 32.4 and a false alarm rate of less than 1 per 80,000 years. It was essentially impossible for this to be a coincidence. By triangulating the slight delays between the three detectors, astronomers were able to narrow down the location of the signal to a specific patch of the southern sky in the constellation Hydra. But the gravitational waves were only the beginning of the story. Just 1.74 seconds after the gravitational wave signal reached Earth, an entirely different kind of detector triggered an alarm. NASA's Fermi Gamma Ray Space Telescope and the European Integral satellite detected a short gamma ray burst arriving from the exact same region of the sky. The probability of a gravitational wave signal and a gamma ray burst occurring simultaneously, by pure coincidence, is roughly 5.0 times 10 to the power of -8. It was a virtual impossibility. These two signals had traveled side by side for 130 million light-years, arriving at Earth less than 2 seconds apart. Within minutes, a global alert was sent to astronomers worldwide, triggering the largest coordinated astronomical observation in human history. Within hours, telescopes on every continent and in space pivoted to search the localization area. What they were looking for was the host galaxy and the glowing wreckage of the collision. They found it in the elliptical galaxy NGC 4993, located approximately 130 to 140 million light-years away. What you are looking at here is the optical transient named AT2017 GFO, a brand new point of light glowing brightly near the edge of its host galaxy. This was the first time in human history that a cosmic event was detected through both gravitational waves and electromagnetic radiation simultaneously. It was the birth of multi-messenger astronomy. Before GW 170817, astronomers essentially had two separate senses to observe the universe. We had electromagnetic radiation, which is light across all wavelengths, a tool we have used for centuries. And we had gravitational waves, our newly discovered ability to feel the vibrations of space-time, proven just 2 years prior. But black hole mergers produce no light. They are completely invisible to traditional telescopes. This event was the first time we could both feel the vibrations of the collision and actually see the fireworks that followed. And by combining these two senses, scientists were about to crack open four of the most stubborn mysteries in all of physics. Let's start with the first massive breakthrough, solving the ancient mystery of where heavy elements come from. For decades, scientists had a fairly solid understanding of the cosmic periodic table. We knew that hydrogen and helium were created in the primordial soup of the Big Bang. We knew that elements up to iron were forged in the nuclear fusion furnaces deep inside living stars. But elements heavier than iron presented a massive problem. You see, fusing elements heavier than iron actually consumes more energy than it releases, meaning a star's normal fusion process simply shuts down when it hits the iron limit. So where did elements like gold, platinum, uranium, and iodine come from? The leading theory was a process called R-process nucleosynthesis, which stands for rapid neutron capture. In this theoretical scenario, atomic nuclei are bombarded with free neutrons so rapidly that the atoms don't have time to undergo radioactive decay. They just keep absorbing neutrons, building up into heavier and heavier elements in a fraction of a second. But for this to happen, you need an environment that is incredibly hot, incredibly violent, and absolutely saturated with free neutrons. For a long time, scientists debated whether supernovae could provide these conditions, or if it required the collision of neutron stars. GW 170817 delivered the smoking gun. When astronomers pointed their telescopes at the glowing wreckage in NGC 4993, they didn't see a standard supernova. They saw a kilonova. As the two neutron stars, estimated to be between 1 Torsor and 189 solar masses each, slammed together, they ejected a massive cloud of neutron-rich matter into space. This ejecta was launched outward at astonishing speeds, traveling between 20% and 45% the speed of light. Astronomers watched as the kilonova evolved exactly as our process theory predicted. They observed two distinct components in the expanding cloud. First was the blue kilonova, which was bright early on and made of lighter ejecta. Then came the red kilonova, which was dimmer, redder, and glowed for days to weeks, powered entirely by the radioactive decay of heavy, newly forged R-process elements. Using the X-shooter spectrograph on the Very Large Telescope in Chile, astronomers analyzed the light from the explosion. If you look a little closer at the spectral lines from this data, you can see the distinct absorption signatures of specific elements. They definitively identified strontium, element 38, marking the first time a heavy element produced by the R process was directly confirmed in a cosmic collision. Evidence was also found for yttrium in the evolving spectra. While directly identifying the spectral signature of gold itself remains difficult due to incomplete atomic data for very heavy elements, the overall brightness and color evolution of the kilonova strongly inferred its massive production. Scientists estimate that this single collision produced roughly 16,000 Earth masses of heavy elements. Included in that cosmic debris was an estimated 10 Earth masses of pure gold and a similar amount of platinum. That means practically all the gold on Earth, the gold in your jewelry, the gold in your smartphone, the gold sitting in bank vaults, was forged in ancient neutron star collisions billions of years ago, long before our solar system even formed. Problem solved. But this one event was far from finished answering questions. The second major breakthrough solved a mystery that had baffled astronomers since the 1960s: the origin of short gamma-ray bursts. Gamma ray bursts are the most energetic explosions in the universe, initially discovered by military Vela satellites that were looking for unauthorized nuclear detonations on Earth. Astronomers eventually categorized them into two types: long bursts, lasting more than 2 seconds, which are linked to the deaths of massive stars, and short bursts, lasting less than 2 seconds, whose origins were completely unknown. For over 30 years, theoretical physicists suspected that merging neutron stars might be the culprits behind short gamma-ray bursts, but they had absolutely no proof. GW170817 delivered that proof on a silver platter. The gamma-ray burst, designated GRB 0817A, arriving just 1.74 seconds after the gravitational wave signal, locked the two events to the exact same source beyond any shadow of a doubt. It definitively confirmed that binary neutron star mergers are the cosmic blowtorches responsible for short gamma-ray bursts. But there was a catch that initially confused the scientific community. The gamma-ray burst detected by Fermi was surprisingly weak for an event occurring only 130 million light-years away. If this was a typical short gamma-ray burst, it should have been blindingly bright. It took subsequent observations from the Chandra X-ray Observatory and the Very Large Array Radio Telescope to reveal the answer. The jet of high-energy particles fired out by the collision was not pointing directly at Earth. It was pointing approximately 30 degrees away from our line of sight. Normally, we only detect gamma-ray bursts when the jet is aimed almost directly at us, much like looking straight down the barrel of a flashlight. But because GW170817 was so close, we were able to view it off-axis, like watching a high-pressure fire hose from the side. This gave astronomers their very first chance to study the internal structure of a short gamma-ray burst jet. It confirmed the cocoon model, proving that these jets have an ultra-energetic, narrow core, surrounded by a broader, dimmer cocoon of material that spreads out as the jet punches through the ejected debris. This realization carries a massive implication for our understanding of the universe. We have likely been dramatically undercounting short gamma-ray bursts for decades, only seeing the rare few that happen to be aimed perfectly at Earth. There are countless more violent fireworks happening out there that we simply cannot see in gamma rays, but that our gravitational wave detectors can now hear. And speaking of hearing the universe, the third major breakthrough from this event provided a brand new tool to tackle the biggest crisis in modern cosmology: the Hubble tension. The Hubble constant is a number that measures exactly how fast the universe is expanding. The problem is, our two best methods for measuring this expansion give us conflicting answers. When we look at the cosmic microwave background, the ancient light from the early universe, we get a value of roughly 67 kilometers per second per megaparsec. But when we use the local distance ladder, measuring the light from Cepheid variable stars and nearby supernovae, we get a value of roughly 73. These values disagree by 5 to 9%, a statistically significant gap that means either our physics is wrong or we are making a systematic error somewhere in our measurements. GW170817 offered a completely independent way to measure the expansion of the universe, bypassing both of the old methods entirely. Because the physics of gravitational waves are so perfectly predicted by general relativity, the signal from a neutron star merger encodes the absolute distance to the source directly in its waveform. You don't need a distance ladder, and you don't need to calibrate it against other stars. This is why GW170817 was dubbed a standard siren, the gravitational wave equivalent of a standard candle. By combining the absolute distance calculated from the gravitational waves with the redshift, or recession velocity, of the host galaxy NGC 499993, measured by optical telescopes, scientists derived an entirely new value for the Hubble constant. The initial 2017 measurement came out to approximately 70 kilometers per second per megaparsec, sitting almost exactly between the two conflicting estimates. By 2023, using refined optical, X-ray, and radio afterglow data, that measurement was tightened to 75.46. While this single event hasn't completely resolved the Hubble tension yet, it has proven that standard sirens are a viable, completely independent tool that could eventually settle the debate once we detect more of them. But perhaps the most profound breakthrough of all was the simplest, and it brings us back to the man who started it all, Albert Einstein. In 1915, Einstein's theory of general relativity predicted that gravitational waves should travel through the universe at exactly the speed of light. For over a century, this fundamental prediction had never been directly verified. Alternative theories of gravity had popped up over the decades, suggesting that gravitational waves might travel slightly faster or slightly slower than light. Over a distance of 130 million light years, even a microscopic difference in speed would result in the gravitational waves, and the light arriving years, or even centuries apart. But they didn't. The gravitational waves and the gamma rays traveled approximately 780 quintillion miles through the cosmos, and arrived at Earth a mere 1.74 seconds apart. This tiny delay is perfectly accounted for by the time it took for the gamma ray jet to break out of the neutron-rich debris cloud after the initial collision. This single observation constrained the difference between the speed of gravity and the speed of light to within 1 part in a quadrillion. It was essentially zero. In one fell swoop, GW 170817 ruled out or severely constrained a whole host of alternative gravity models, including scalar tensor theories, Hojava-Lifshitz gravity, bimetric gravity, and theories involving extraspatial dimensions. It was one of the most stringent tests of general relativity ever performed, and once again, Einstein was right. When you step back and look at the sheer volume of data extracted from this single event, it is easy to see why scientists universally refer to GW 170817 as the Rosetta Stone of astrophysics. Just as the original Rosetta Stone allowed historians to decode 3 ancient languages at once, this single collision decoded 4 major cosmic mysteries simultaneously. It gave us the origin of heavy elements, the nature of short gamma-ray bursts, a new tool for the Hubble constant, and the ultimate proof of the speed of gravity. But the data also allowed physicists to peer inside the neutron stars themselves. By analyzing exactly how the gravitational wave signal changed during the final few orbits, scientists could measure how the 2 neutron stars deformed each other tidally. This tidal deformation allowed physicists to place strict constraints on the mysterious equation of state, proving that neutron stars are relatively compact and ruling out theories that predicted extremely large radii. It also helped constrain the maximum possible mass of a neutron star to approximately 2.1 to 2.16 solar masses. As for what happened to the merged object after the collision, the final twist in the story is that it likely didn't stay a neutron star for long. The combined mass of the system was 2.82 solar masses, which is too heavy to remain stable. Scientists believe the collision briefly formed a hypermassive neutron star, spinning wildly to fight off its own gravity, before inevitably collapsing inward to form a brand new black hole. The sheer scale of the scientific response to this event is staggering. Over 70 observatories on every single continent, including Antarctica, participated in the follow-up observations. The initial discovery paper published by the LIGO and Virgo collaborations featured approximately 3,500 authors. It was a truly global achievement, rightfully named the Breakthrough of the Year in 2017 by the journal Science. But as we look to the future, GW 70817 serves as both a triumph and a tantalizing tease. As of 2026, this event remains the only confirmed multi-messenger neutron star merger we have ever observed. Other candidates have been detected by LIGO, but they didn't produce visible electromagnetic counterparts, possibly because they collapsed into black holes too quickly, or because they were located in unfavorable patches of the sky. But the silence won't last forever. With the ongoing LIGO observation runs, and the planned construction of next-generation detectors like the Einstein telescope in Europe and the Cosmic Explorer in the United States, our ability to hear the universe is about to become exponentially more sensitive. These future facilities will be able to detect neutron star mergers from much greater cosmic distances, promising a wave of new standard sirens that could finally put the Hubble tension to rest. And as our optical telescopes and spectrographs improve, we may soon be able to definitively isolate the spectral signature of gold itself in the glowing embers of future kilonovae. The universe is a violent, chaotic place, filled with unimaginable extremes that destroy and create on a scale we can barely comprehend. But the next time you hold a piece of gold jewelry, take a moment to really look at it. You are holding the direct result of two dead stars colliding at a fraction of the speed of light, billions of years ago, in a galaxy far away. It is a quiet, beautiful reminder of the cataclysmic events that shape our cosmos, and a testament to the incredible ingenuity of the human beings who figured out how to listen to them. Thanks for watching.